Today, we want to learn how to solve some more triangles. Right now, our solving triangles game is limited to right triangles. Remember, in the solving triangles game, I give you 3 pieces of information and you find the other 3. This is a given 3, find 3 game. So that's the solving triangles game. Given 3, find 3. Solving triangles means given 3, find 3. I give you 3 parts. You find the other 3 parts. There are 3 angles and 3 sides. I have to give you 3 of those things in some combination that's not just 3 angles, and then ask you for the rest of the stuff. So far, we've played the right triangles game. And the tools that we have for solving right triangles is the Pythagorean theorem. Opposite squared plus adjacent squared is equal to hypotenuse squared. Usually we call this a squared plus b squared equals c squared. And we have our trig functions. The sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. Tangent of theta is opposite over adjacent. The sine and cosine involving hypotenuse means that we're in a right triangle. And when we say tangent of theta is opposite over adjacent, we are talking about a right triangle. Because if we're going to call one of the sides adjacent to the angle, that means the other side must be the hypotenuse. So that the tangent of theta opposite over adjacent only works for right triangles. So we had tools for right triangles, and we had one tool that worked for any triangle, which was that the sum of the angles is 180 degrees. This is all stuff that we did way back when, and so we remember this stuff. What we want to do today is expand our tool set for solving any triangle. Specifically, we're going to solve non-right triangles known as oblique triangles. So we're going to get some new rules for solving triangles. We have that the sum of the angles is 180 degrees. That works for any triangle, including right triangles. We use it in solving right triangles. But now we're going to be solving any triangle where we can't use the Pythagorean theorem and we can't use opposite adjacent hypotenuse. So here, the point is that we no longer have opposite adjacent hypotenuse. Now we have to deal with what if we have an oblique triangle. Oblique just means not a right triangle. Oblique just means non-right triangle. And what we mean here is that we don't get to use opposite adjacent hypotenuse. We are going to refer to sides as adjacent sides and sides opposite an angle, but we can't use the opposite adjacent hypotenuse stuff. We can't use the Pythagorean theorem, and we can't use sine of theta is opposite over hypotenuse because there won't be a hypotenuse in an oblique triangle. So there are 2 new things that we need. We need to add 2 more things to our tool set. One corresponds to Pythagorean theorem, the other one corresponds to trig functions. Here are the 2 new tools that work in any triangle. One of these is the law of cosines. The law of cosines is the general Pythagorean theorem. It's Pythagorean theorem plus. So if we want to solve an oblique triangle, don't have a hypotenuse, can't use Pythagorean theorem. It's right there in Pythagorean theorem. The sum of the squares of the legs of a right triangle is equal to the square of a hypotenuse. If we don't have a right triangle, we don't have a hypotenuse, we can't use that. So for that, we have the law of cosines. It's Pythagorean theorem plus. So we're going to need to open up the WebSmart app on your phone and unlock access to the law of cosines. I'm just kidding. I'm just trying to think about future math classes. So I thought to unlock the next law, to unlock the law of cosines, subscribe to Trigonometry Plus. Now, the Pythagorean theorem we think of as, a lot of times we think of that as a squared plus b squared equals c squared. If we have a hypotenuse is c and adjacent is a and opposite is b, or the other way around. We think of the Pythagorean theorem as c squared is equal to a squared plus b squared. In the law of cosines, we start off with that. Well, we only start off with that. This is a but wait, there's more scenario. So we write c squared is equal to a squared plus b squared. And then we write the law of cosines term, which is minus 2ab cosine gamma. So c squared is a squared plus b squared minus 2ab cosine gamma. I scrolled past the triangle that I wrote at the beginning. So I can't just have c squared equals a squared plus b squared. That's the Pythagorean theorem. That's for right angles. That's if this gamma angle is 90 degrees. If it's not 90 degrees, I have to have minus 2ab cosine gamma. Notice that if gamma is equal to 90 degrees, then c squared, c is the hypotenuse, and the cosine of 90 degrees is 0. So this term drops out. So this is the better version of the Pythagorean theorem. If gamma equals 90 degrees, then this is a right triangle. C is the hypotenuse, and the cosine of 90 is 0. So we end up with the Pythagorean theorem. So the way we upgrade the Pythagorean theorem is to add that term, minus 2ab cosine gamma. There are two other versions of the law of cosines for sides like this. There are two other versions. Instead of c squared equals a squared plus b squared, I can have one that has b squared on one side. I can have a version of the law of cosines with a b squared instead of a c squared. So just trade the b and the c. Just permute things around. So I could write b squared is equal to a squared plus c squared. And I have to change this term as well. Minus 2ac times the cosine of not gamma, but beta, because beta is opposite to b. So here's the b squared version of the law of cosines. And of course, we should see the next part coming. There's an a squared version of the law of cosines as well, where we have a squared. Now I'm just going to trade the a squared, the b squared. A squared equals b squared plus c squared. And then my other term will be minus 2bc times the cosine of alpha. A time when we will use this version of the law of sine is when we have information that fits. And that will be the category of two sides and the included angle. So we're going to use the law of cosines. We're going to use this version of the law of cosines if we have two sides and the included angle. This is known as the SAS case. I spelled when wrong. So we're going to use this law of cosines when we're given two sides and the included angle. That means the two sides that make up that angle. So that would be like, if we're given A and B, we also have gamma. That's this case, A, B, and gamma. Or if we're given A, C, and angle beta. So angle A, side C, angle beta is included. So A, C, and angle beta. Or because rule of three, B, C, and angle alpha. in this description. So we're going to do this when we have two sides and the included angle. Notice that we have like one of each, one of the A's, one of the B's, and one of the C's. A, B, and gamma corresponds to C. A, beta corresponds to B and C. Alpha corresponds to A, B, and C. So we got a one of each, with one of them being the angle. Sometimes this is abbreviated as the SAS case because we have two sides and the angle in between those sides. So we abbreviate this SAS. We have two sides and the angle between those sides. Side A and B and gamma, which is made up of A and B. A and C and angle beta. B and C, angle alpha. That's SAS, two sides and the included angle. It's a super Pythagorean theorem. It's the Pythagorean theorem plus. It's the better version of the Pythagorean theorem. Let's do an example. An example where we're going to use the law of cosines. I've got two sides and one angle, and the angle is in between the two sides. Got side A, I got side B, and gamma is the angle between side A and B. So two sides and the included angle. We're going to use this, and since we have A and B and gamma, we're going to use the law of cosines, and it's the only thing that we have available to us right now. And we're going to use it to solve for C. The first thing that we have to solve for is C. It's the only thing that we can find first. So C squared is equal to A squared plus B squared minus 2AB times the cosine of gamma. So C will be the square root of A squared plus B, which is 21.0 squared, minus 2 times A times B times the cosine of 37. And then if I take the square root of all that, that will be C. So C squared is equal to that stuff. So C is the square root of that stuff. The good news is we can type this like we see it. If we have a graphing calculator, like a TI-84 plus CE, purchased from, I don't know I got this. I don't get sponsorship from Texas Instruments or anything like that. It's just the calculator that I happen to have. It's pretty effective. If you get one, it'll work all the way through like linear algebra and stuff. So not a sponsored post, but we'll just do the square roots of 13 squared plus 21 squared minus 2 times 13 times 21 times the cosine of 37. That's going to close the cosine. That closes the square root. And before I hit enter, I want to make sure I'm in degree mode. And there's the other side, 13.2. One of the things that we want to note here is that this was the only thing that we had available to solve for. This is the only thing that we could try to find first. Anything else that we tried to find, we don't have the information. So note, this is our only choice to start. Based on the given information, we had no choice but to go after C first. It was the first thing that we had to find. We didn't have enough information to find anything else. The other version of the law of cosine says b squared is a squared plus c squared minus 2ac times the cosine of beta. If I wanted to use this to find b, oh, I have b already. If I wanted to use this version of the law of cosines, this entry in the law of cosines, this requires beta, and we don't have beta. The other version of the law of cosines would have required alpha. Where it says a squared is equal to b squared plus c squared minus 2bc times the cosine of alpha. And here, we don't have alpha. And really, I wrote those down not just to point out the things that we don't have, but also to write down the law of cosines again. Thus subtly tricking you into writing the law of cosines a second time. Teaching is really just manipulation. At this point, we've also exhausted our law of cosines uses, because or in this form anyway. So we don't have beta, we don't have alpha, so we have to use that. C squared equals a squared plus b squared minus 2ab cosine gamma. We had to use that because gamma was the angle that we had. There is another way we can use the law of cosines. Another way to use the law of cosines is to find an angle. So we'll call this B2. We can use the law of cosines to find an angle. All we have to do is take the law of sines and turn it around. What we're going to do is take the law of cosines and we're going to solve for the angle. We're going to be solving for an angle, so we know that an inverse trig function is going to show up because that's how we find angle. We use inverse trig functions. So let's just get the cosine of gamma by itself and then cosine inverse. So if we subtract c squared and we'll subtract a squared and b squared, then we'll divide by the negative 2ab. Then we're going to notice that we divided by a negative 2ab. We're going to look at that negative hanging out in the denominator and we're going to go, ew, that looks terrible. You might think the whole thing looks terrible, but I want you to specifically focus on this negative 2ab and say, that looks bad. So everybody look at that. That looks bad. I'm trying to manipulate. I'm actually not trying to manipulate. I'm directly telling you what you are supposed to think when you look at a negative in the denominator hanging out like that. So, that looks terrible. So I want you to think, oh, this is a Challenger, and they left those little yellow those little yellow things on it. And they go, oh man, that looks like shit. Take those things off. They're to protect the splitter during transport. They're not supposed to be left on the fucking car. That looks bad. If you have them on your car, I better not find out because I'll just fucking flunk you. Like right away. I see you driving in your Challenger or your Charger and you got the little yellow things on. I'm like, drop the class now. I'm just kidding. It's just a matter of taste. Bad taste. So I look at that and it's like, nasty. Yeah. Yeah, the dealer's supposed to take them off, but when people get their car before they take delivery, some people wanted them to be left on. So they call the dealer, don't take those things off. It's like, oh, why? Look cool. I think you're wrong. I'm just kidding. If you think they look cool, then no, not kidding at all. If you think they look cool, you're incorrect. Because it's like safety yellow. You know what I mean? I've seen some people pull those off, plastic dip them in a different color and put them back on. Like, I think a lot of people. They don't tell you. Yeah. It's like, oh, it'll be fine. It's like when people like drive around with a little sticker on their car that says, hey, this vehicle is equipped with like some anti-theft radio. So like an 8-year-old car, and they have a little sticker on the side. It's like, well, don't try to steal this radio. It'll stop working. It's like, well, you're kind of supposed to. Or like the version of that, if you don't pay attention to cars, that's cool, that's cool. That'd be like if you get a phone and it still has like the plastic stuff on the front of it. So like someone's like picks up their phone and like texting and shit like that, and as you see a little plastic tab, like for those of you at home, little plastic tab here, it's like, oh, did you not pull the plastic film off your phone? And you're like, oh, what are you talking about? And then you start doing it, and then they can't stop doing it because now it's halfway off. So if you see someone with that shit on their phone, like start pulling it. It's like, well, now you have to take it off. And if they're like, oh, no, I'm just gonna leave it as it is, then they're just not your friend anymore. It's like, oh, throw your hands up, walk away. Sneak into their house and take it off. Film. So this negative looks terrible. Does everybody agree that this negative looks terrible? It's like, oh man, it's terrible. So what we're gonna do is we're gonna multiply everything by -1, because that'll make the denominator positive. And see this like 3 negatives? Like, ooh, 3 negatives. We're gonna cut that down to like 1 negative, right? Because this is America, you all have to be happy, god damn it. Less negative, more positive. You're not allowed to be sad or angry or shit like that. This is America. Be positive. And let's increase the toxicity. Like, oh, why just be positive? Like, oh, fuck you, I'm mad. Because someone's driving around with little yellow bumper guards on their fucking Challenger. Taking an awesome looking car, making it look bad. I don't know why I care so much. I don't think I do. So we're just going to drop a -1 bomb. I'm going to change the sign of everything. You change the sign of all the terms on top, change the sign of the terms on the bottom, then you can just change all the signs. So it looks like this. I'm going to have like a positive a squared, so I want to write that first. A positive b squared now, and only c squared is negative. And in the denominator, we have a positive 2ab. So overall, we have much more positive stuff. Don't worry, be happy. Be happy. So c squared is all negative now, but everything else is positive. Now, if I want gamma, I can just cosine inverse both sides. How's everybody okay? Everybody's thinking about how cool challenges are. I say I admire Dodge as a car company just because it's like, oh, they have like essentially like 3 cars that just haven't changed. Like they released a Challenger in like 2008. It's on the same platform as the Charger. It came out even sooner than that. And they're like, oh, are you going to change this? And they're like, oh, nah, we're just going to put more power into it. That's it. That's all they've done. Put bigger and bigger, actually just more powerful engines in it. So are you going to update this shit? And they're like, oh, nope. We're going to keep selling the same car. It's going to put an unreasonable amount of power into it. Question? Not about Dodge, but about the law of cosine. Okay. Any questions about Dodge? I have a question. Can you put the Hellcat engine in a Miata? They did it with Prius? That is dope. Did they put it in the middle? Okay. They do all kinds of stuff. There's a company that will put an LS engine into your Miata. If you bring them a Miata, they'll put an LS into it. If you bring them a Miata from 95 or sooner, they'll put an LS into it. That will be carb legal. So you can drive it, register it, and drive it around in California. I mean, you're only going to get like it's like 420 horsepower, but it's a fucking Miata. A V12, that is great. I think everything should come with a V12. Oh, that'd be awesome. That'd be awesome. I'd love to put an LS in the Prius, especially if you take because the Prius is like the hatchback is a hatchback. So that's a perfect place to put a fucking engine. Take the four banger out the front, take out the back seats, put an LS in there. Brilliant. Oh man. They made a visual render of a Hellcat Dodge Caravan. The problem is the Pacifica or the Dodge Caravan, the engine's mounted sideways on the front wheels. So you'd really have to do a lot of work, turn the engine 90 degrees, put in and have it rear wheel drive. But they can take the Durango and just kind of like I wonder if they could just take a Durango, take the body off the Durango and slap the Pacifica on it and have a Hellcat minivan. I'm going to call Dodge. Tell them how many minivans they would sell if the minivans had 700 horsepower. Oh, dude, you got to do this. Anyway, what are we talking about? Oh yeah, the law of cosine. Nice. Big old drivetrain, like right down the middle of the minivan. What's all this? Nothing. Just sit down. Crash into the crowd of cars and coffee, like a Mustang. There are two other versions of the gamma, and we could just do permutations like we did with the B squared and the C squared. So notice that the gamma and the C, those are the that's an opposite pair. And then the A squared plus B squared and the 2AB, that's the stuff that matches. So if I wanted to do a gamma version of this, or sorry, a beta version of this, we'd have a cosine inverse. The denominator would be, the negative term would be a minus B squared. That's where the matching happens. That's where the matching happens. Beta and then the B squared, just like the gamma and the C squared. So the rest of it would just be A squared plus C squared, the stuff that doesn't match. And then the denominator is those two, 2AC. And then, of course, because there are three and you have to do all three of them, there's an alpha version with a cosine inverse. And alpha goes along with A, so that's going to be alpha and a minus A squared. So the positive stuff, the stuff that got turned positive, that's all the other stuff. A and alpha go together. So it'll be a B squared plus C squared. And in the denominator, a 2BC. So patterns everywhere. Now notice that in these three, we're solving for an angle, and the information that we have in solving for an angle is all three sides. So this version of the law of cosines is when we have all three sides, and we can use all three sides to find any of the angles. And we call this the SSS case, because we have a side, and a side. And we get the flexibility here is that once you have all three sides, you could use this to find any of the angles. Let's pause here, take a quick break, come back and do an example. We have all three sides.